The last topic in this section is the osculating circle. Now, I referred to this when we were studying curvature. I said the osculating circle was like the round version of the tangent line. It's going to be the circle that best approximates a curve at a particular point. Now, with a circle, I need to know two things. I need to know the radius, and I need to know where to put the center. Okay, so the radius, let's say we're talking about the osculating circle at a point r of t naught. Okay, so the radius is just going to be the reciprocal of the curvature at t naught. Okay, remember we said that a circle of radius a had a curvature of 1 over a. So there was this reciprocal relationship between curvature and radius. So what I'm trying to do here is I'm going to create a circle at this point whose curvature is the same as the curve at that point. Okay. Now, where do I put the center? Well, I want the circle to, let's say this is my r of t naught. I want the circle to actually pass through this point. So here, the osculating circle would be the circle that best lined up with the curve. It would look something like so. So I can see that I want that center to be on the concave side of the curve. Okay. So here's where I'm going to take advantage of the fact that if this is my unit tangent vector, in 2 space, the unit normal vector always points to the concave side. Now in 3 space, the concave side is not particularly well defined. But in 3 space, the osculating circle will lie in the Tn plane. And so we want to go in the direction of n. Okay, so this will be 1 radius away from r of t naught in the direction of the unit normal vector at that particular point. Okay, and that's going to give us the circle that passes through that point. It's going to have the same tangent and normal vector and the same curvature as the curve does at that point. So it really is like the round version of a tangent line. Okay. What I'd like to do is just do one example. And I'm going to first of all just graph the osculating circle by inspection, because I might ask you to do that. I might ask you not to calculate anything, but just to draw it, just to eyeball it, the same way we can sort of eyeball a tangent line. And then I want to actually calculate it and see how close my eyeballing of things was. So let's suppose I've got the curve r of t equals 2 cosine t, 3 sine t. Now, I recognize that that's just a morphed circle, otherwise known as an ellipse. We essentially took our unit circle and we stretched our x values by a factor of 2 and our y values by a factor of 3. So we're getting an ellipse that looks something like so. Okay. Now, I'm going to try to find the osculating circle at this point right here. That would be when t is pi over 2, because notice then I'd be at 0, 3. Okay. So I'm going to try to just sort of eyeball and draw in what looks like the osculating circle at that point. Okay. Now, I don't think this is perfect by any stretch of the imagination, because I don't think that my ellipse was perfect. But you'll notice that I've tried to match up so that the circle almost looks like it completely agrees with the ellipse for as long as possible. It doesn't actually completely agree, but it's close enough that you can't really tell with the naked eye. Okay. Interesting trivia fact. The word osculating means kissing. So essentially, the mathematical advice that we get there is that you want lots of contact when you're kissing. We're not talking just a little peck, good contact. Okay, All right, so let's see if we can't actually now calculate that. Now, I've chosen this point on purpose because I know that this is oriented counterclockwise because I've got cosines in the x position and sines in the y position. So I can see just by inspection that the unit tangent vector at the top is horizontal, and therefore I know it's pointing to the left. I can also then see by inspection that the unit normal vector is going to be pointing straight down. So I'm not going to have to calculate that. I'm going to find that by inspection. I'm going to need to find my radius, which will be the reciprocal of my curvature, and then I'll need to go that far down from this point up here, which would be 0, 3, to get to the center of that circle, and I'll also know my radius. Once I know the center and the radius, I can get the equation. Okay, so I'm going to embed things in 3 space so that I can use the cross product formula for finding my curvature. So we're going to go to r tilde of t, which would just be 2 cosine t, 3 sine t, 0. Then r tilde prime of t would be negative 2 cosine t, I'm sorry, negative 2 sine t, 3 cosine t, 0. And r tilde double prime of t would be negative 2 cosine t, negative 3 sine t, 0. Okay, now I'm wanting to find the curvature at pi over 2. I'm going to use the formula that kappa of t is the magnitude of, in this case, r tilde prime crossed with r tilde double prime over the magnitude of r tilde prime t cubed. Again, a formula you don't need to have memorized. You might accidentally memorize just by using it often enough, and I certainly don't object to that. But I generally memorize it whenever I teach this class and then forget it before the next time I teach the class, and then memorize it again, and it comes and goes. Okay, notice what I'm doing here just involves taking a cross product and magnitude. I'm done taking derivatives. So if I want, I can go ahead and plug in pi over 2 before I take the cross products and the magnitudes. And that's just some strategic laziness. I kind of like to do that. So let's see. I'm going to just start this the top of the board up here. So r tilde prime at pi over 2, I'm going to be getting sine of pi over 2 would be 1. So this is going to be negative 2, 0, because cosine of pi over 2 is 0, and 0. Okay. So negative 2, 0, 0. R tilde double prime at pi over 2. Let's see, cosine of pi over 2 is 0, so now that's 0. Sine of pi over 2 is 1, so this is going to be negative 3. So we're getting 0, negative 3, 0. Excellent. So now let's calculate that cross product that I need. So r tilde prime at pi over 2 crossed with r tilde double prime at pi over 2 is my symbolic determinant, I, j, k, negative 2, 0, 0, 0, negative 3, 0. The i's are going to be 0 minus 0 is 0. The j's, 0 minus 0 is 0. And I knew I was going to get that because both of these vectors were in the xy plane. Their cross product, if it's not 0, has to be parallel to k. Okay. So, let's see. For the k's, I get 6 minus 0 is 6. Excellent. Okay. So now, I can see pretty much by inspection, the magnitude of that is 6. So, if I look at the magnitude of r tilde prime at pi over 2 crossed r tilde prime, double prime at pi over 2, that's just 6. And if I look at the magnitude of r tilde prime at pi over 2, I can also get that by inspection. That's just 2, because that's just a vector that points 2 back. So that's 2. Okay. So my curvature at pi over 2 is 6 over 2 cubed. That's 6 over 8, or 3/4. Now if that's the curvature, that means that the radius of my osculating circle is the reciprocal of that. So the radius of my osculating circle is 4/3. So what I drew freehand looks pretty reasonable. It's not perfect, but it looks like I had a radius that was a little bit bigger than 1 just by sort of eyeballing it, and the radius is a little bit bigger than 1. Did I get it perfect? Of course not. But if I ask you just to sketch something by eyeballing it, that's the sort of thing I'm looking for. Did you make it so that your circle really lines up with the curve as much as possible? Now, what would the center be? Well, we were supposed to go this distance in the direction of the normal vector. So starting here, which was at the point 0, 3, I need to go 4/3 down. So that's going to be 0. 3 would be 9/3, minus 4/3 is 5/3. So if I wanted my equation for the osculating circle, it's just going to be x squared plus y minus 5/3 squared is equal to 16/9. Don't forget, it's the radius squared. Okay, kind of neat.